Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 21st, 2025, just 5 days ago. This paper presents a new method that reduces the tokens a model uses by up to 40.9%, while actually improving its accuracy. The paper is titled, LAPO, Internalizing Reasoning Efficiency via Length Adaptive Policy Optimization, and it tackles a common problem with large models in a really clever way. It addresses the issue of models overthinking simple problems by teaching them to adapt their reasoning length to the task's complexity. Also, the authors shared their implementation on GitHub. Over there, you'll find the complete framework for what they call hierarchical budget policy optimization. It includes all the training and evaluation scripts, data preparation tools, and detailed instructions to get started and replicate their impressive results on reasoning efficiency. This first figure gives a great overview of the whole process. On the left, it shows the two-stage training method, which uses reinforcement learning, a technique where the model learns by getting rewards for good behavior. First, it discovers the natural length for a correct answer. Then, it learns to plan ahead, proposing a token budget for itself. The plot on the right shows the payoff. The vertical axis is pass at 1, which is the percentage of problems the model solves correctly on its first try. You want to be in the top left, high accuracy, low tokens. And that's exactly where the LAPO models land, outperforming the others. So let's break down how they achieve that result. This diagram details the two-stage process, which uses Group Relative Policy Optimization, or GRPO, a method for training the model by comparing different possible answers. In the first stage, discovery, the model generates several potential solutions. It then analyzes the successful ones to find a good, efficient length, getting a reward for being both correct and concise. This process builds a map of problems to ideal lengths. Then, in the internalization stage, it uses that map to propose its own token budget before starting, and gets rewarded for sticking to that plan. Moving to the results, this table shows the hard numbers. It compares the LAPO method against base models and other efficiency techniques on several math benchmarks. We see two key metrics, pass at 1, which is the percentage of problems solved correctly on the first try, and the number of tokens used. Look at the DeepScaler R1.5b preview model group. The final LAPO I model achieves the highest average accuracy, 64.8%, while using nearly 40% fewer tokens than the original base model. This is a huge win, improving accuracy while drastically cutting down the work the model has to do. Building on those efficiency gains, this next figure shows how the models learn to be so smart with their tokens. It plots the average reasoning length against problems of increasing difficulty, from Math Level 1 up to the much harder AIME 2024 problems. And for both the DeepSeek R1 and DeepScale R models, you can clearly see a near linear trend. As the problems get tougher, the models allocate more tokens. This scaling behavior shows the model isn't just cutting corners. It's developing an intrinsic ability to gauge a problem's complexity and adjust its effort accordingly. So, in conclusion, this work on length adaptive policy optimization is really impressive. It moves beyond just forcing models to be shorter. Instead, it teaches them an intrinsic sense of a problem's difficulty, allowing them to plan their own reasoning budget, much like a human expert would. This approach refines the model's chain of thought sequences, which are the step-by-step reasoning paths models follow to reach an answer. By optimizing these paths, the method achieves that rare double victory, a massive drop in token usage and a simultaneous boost in accuracy. That's all for this week's AI Research Roundup. Thanks for tuning in.